everyone, welcome to this explainer. I am absolutely thrilled you're here today because, well, we're going to connect two completely different worlds that secretly rely on each other literally every single second of the day. Have you ever stopped to think about the sheer physical weight of your digital footprint? Like every time you click accept all cookies on a website, you kick off this massive invisible data harvest. But here's the thing, that data doesn't just float around in some magical weightless cloud. It has a real physical reality. Today, we're going to trace the journey of your personal data, starting from those abstract digital consent forms on your screen, all the way down to the heavy, brutalist engineering sitting at the very bottom of the ocean. Okay, let's dive into this. 1,022. Just think about that for a second. That staggering number represents the exact amount of advertising partners listed on just one standard website's privacy and cookie consent form. Yeah, no joke. When you casually hit accept to read an article or watch a video, you're instantly granting up to 1,022 different entities permission to process your personal data.
And look, we aren't just talking about some vague idea of what shoes you like to buy. These partners are harvesting highly specific metrics. They're logging your IP address. They're actively scanning your device for specific characteristics to create a unique fingerprint of your exact phone or laptop. And they're recording your browsing interactions. They are even tracking your precise geographical location, often accurate to within 500 meters. This massive web of data is combined, profiled, and then stored for months across hundreds of different vendors. And the whole shebang is just to serve you personalized ads and content.
But here is a massive disconnect, right? We kind of just assume all these profiles, ad bids, and location pings are happening somewhere up in the ether or the cloud. But to actually get from your device, sitting there in your living room, to the servers of these 1,022 partners scattered all over the world, how does that data physically travel across the globe? Well, it requires heavy, tangible physical infrastructure. Basically, our modern digital lives, including every single one of those cookie trackers we just talked about, rely entirely on incredibly robust engineering hidden deep beneath the waves. So let's quickly take a look at the anatomy of one of these subsea cables. To actually move the internet across oceans, a subsea cable really has two distinct primary jobs. First up, it has to transmit light over optical fibers. This is the actual data itself. Your cookies, your streaming video, your emails, it's all encoded into light. Second, the cable has to act as a massive literal extension cord. It conducts an electrical current to power the system's repeaters, and those repeaters boost the light signal along its journey. Now, in massive modern infrastructure projects, like the upcoming SMAP system, we are talking about electrical currents exceeding 10 kilovolts. That is a seriously powerful extension cord. Now, laying a cable carrying 10 kilovolts of electricity and super delicate light signals isn't happening in some safe, climate-controlled server room. The ocean floor is, quite frankly, an incredibly hostile environment. Engineers literally have to solve for immense environmental threats. The cable must withstand the crushing pressure of water up to 8,000 meters deep. It has to survive the corrosive power of seawater, resist being cut or crushed by dropped ship anchors, rock falls, or commercial fishing lines. Plus, it needs the tensile strength to survive the sheer physical stress of being suspended from a cable-laying ship and dragged around by seafloor currents.
Okay, moving right along, let's talk about forging the glass heart of this whole operation.
So, how do you transmit the world's data through that kind of nightmare environment? Well, we have to zoom way, way in to the microscopic core of the cable where data actually lives. And this brilliantly illustrates the central paradox of our whole digital world. The core of this massive, robust system is actually incredibly fragile. We use what's called single-mode optical fiber, or SMOF. This is a continuous core of highly pure silica glass. By manipulating the refractive index with different chemical dopants in the glass, engineers create a perfect pathway. It's totally optimized to shoot light over thousands of miles at around the 1550 nanometer wavelength. So yeah, your data is literally traveling through glass. And to fully grasp the scale of this, 125 micrometers. That is the ultimate diameter of this optical glass fiber. It is literally fractions of a millimeter wide. We're talking thinner than a human hair. Making a glass thread that thin and that pure is an absolutely incredible sequential process. First, high-purity silica glass is formed into a hollow tube called a preform, where different dopants are carefully added. Next, this preform is sintered, basically heated and pressed into a solid glass blank. Then, in step 3, things get really extreme.
The blank is suspended in a massive drawing tower, heated to over 2,000 degrees Celsius, and drawn out until it hits that microscopic 125 micrometer diameter. Instantly, in step 4, a thin polymer protective coating, or buffer, is applied to give it just a little bit of shock resistance, beefing it up slightly to about 250 micrometers. Then it's wound onto these massive spools holding up to 250 kilometers of fiber before finally being shipped off to the cable manufacturer for assembly. All right, next up, armoring for the deep. How exactly do we protect this thing? Because once the cable manufacturer has this fragile, hair-thin glass heart, the next monumental task is protecting it from, those anchors, rocks, and crushing pressure we talked about earlier. It happens in layers, and each layer is a targeted engineering solution. The construction of the foundational lightweight or LW cable base starts with the delicate raw fibers placed inside a welded stainless steel or polymer tube, and that tube is filled with a special gel to absorb shock and block water. Second, that tube is wrapped in a heavy steel wire vault, which provides the immense tensile strength needed just to lay the cable. Third, copper tape is seam welded completely over those steel wires. Together, the copper and steel form the conductor that carries those 10 kilovolts of electricity. And finally, a thick polyethylene layer is bonded to the outside to completely insulate that high-voltage electricity from the surrounding seawater. Now, what's really interesting about this is seeing how the physical armor scales up aggressively depending on how risky the ocean environment is. That lightweight base we just looked at, that's just the starting point. If the cable needs extra abrasion resistance, they upgrade to lightweight protected, or LWP, which adds steel tape and an extra high-density outer sheath. But what if the cable is going into shallow, high-risk waters where fishing nets and dragging anchors are super common? Well, they wrap the whole thing in single or double armor. That is literally 1 or 2 extra layers of heavy, galvanized steel wires covered in industrial tar and yarn. Okay, let's bring it all together and look at the final subsea journey. So, we've tracked the data from that abstract consent form right down to the microscopic glass and out through the heavy steel armor. When you pull back and look at the real-world scale of one of these finished systems, honestly, it's almost difficult to comprehend. For instance, the upcoming SMAP trunk system will span a massive 5,200 kilometers across the ocean floor, linking Sydney all the way to Perth, with branches to Melbourne and Adelaide. Just imagine all of those microscopic 125 micrometer glass threads stretched continuously across a continental scale. It's wild. And because our modern reliance on these systems is literally absolute, the engineering has to be completely uncompromising. The SMAP system is actually achieving a fascinating world-first engineering milestone. According to the developers, the SMAP cable system skips the standard unarmored lightweight cable entirely. It's going to be the first fully armored submarine cable in the entire world, utilizing lightweight protected-grade cable across its entire 5,200-kilometer length. Which basically brings us right back to where we started. The next time you click a cookie consent banner and 1,022 advertising partners instantly start profiling your precise 500-meter location and your device fingerprint, remember this explainer. Remember that your data isn't just floating in a cloud. It's shooting as light through a microscopic thread of pure glass, protected by heavy steel and tar, sitting in freezing darkness thousands of meters beneath the waves. So is it surprising that the massive, heavy footprint of our modern digital data relies entirely on the survival of that incredibly fragile glass thread at the bottom of the ocean? Thank you so much for exploring this with me today, and I really hope this leaves you with a totally new perspective on your digital world. Catch you next time.